So there are a bunch of laws that we can use with limits. This is similar to like our log rules and so on and so forth. So there's going to be some conditions. So say C is some constant. So meaning some constant number. And and so C being a constant also means it's not infinity and it's not negative infinity. And limit as x approaches a of f of x, and the limit as x approaches a of g of x both exist. So here a could be infinity, a could be negative infinity, a could be some constant, um, but the limits of these functions exist. Okay. So what are our laws? Okay. So our first law, which, we kind of had a feeling of last class, is we can split over addition if the two limits exist. Okay, so if the limit of f didn't exist, it doesn't make sense for us to distribute over addition, right? Because then what would this mean? Don't have enough space, so let's move that down. And for those of you who are just joining, because I think I just saw a surge of new students, it is recording, but is only recording me. So if the limit of one of these things didn't exist, this wouldn't really make a lot of sense, right? So say limit of f of x didn't exist, then distributing the limit over the addition doesn't make sense because then I have a does not exist plus like 7 or something, whatever the limit of g is. And what does that mean? Right? Does not exist doesn't add to something else, right? It could be that this whole limit here maybe doesn't exist if f doesn't exist. It could be some like surprising thing they cancel out. Who knows, right? Our second law is basically the same thing just with subtraction. And these brackets that I'm putting is just to sort of make sure that everybody's on the same page, that the limit is on the whole thing, is on f of x plus plus g of x total. So if we have a subtraction, yeah, same thing. Third is if, oh great, okay. Now I sound like a person. Okay. If I had, oh, I guess I was using brackets. Let's keep using brackets, maybe. You don't need to use brackets. It's just sometimes it's nice that something looks different. Okay, so if I have c times a function, I can pull that c out. So remember, c is just some number. It's not infinity, it's not negative infinity, it's just some number. Okay, so that's nice. All right, what's next? And then this one is multiplication. But this one's really, really important that this is only true if each piece exists. Because I feel like the addition one maybe makes more sense to people that like, oh yeah, like maybe I'll need to simplify or something if like one part doesn't exist. But this one, people just start to go into it and then they're like, at least I've seen this in students' works before. They go into it and then they get like some weird answer and they're like, oh boy. I don't know what the answer is. Maybe it does not exist. But the answer is, oh, you weren't allowed to split the limit at the beginning. Okay. And so we'll do some examples because we need to demonstrate that, here, maybe I'll put these ones in brackets now, that each piece of the limit does exist in order to split it. Okay. So division now, as maybe hopefully I've taught you by now, we need to be a bit more nervous about. Okay. So I've got f of x divided by g of x. And, if we were in class, I'd be like, oh, like what are we scared of? And, someone would say dividing by 0. So we can split this. We get split limit over division if both the limits exist and if limit of x, limit of g of x is not 0. Oop. Oh my gosh. Okay. And hopefully that makes sense, right? Because, okay, in order for each of the pieces to make sense, right, they need to both exist, or else I have like does not exist divided by 17. Like, what is that? I don't know. Um, but then, but then I also don't want to accidentally divide by 0, right? That'd be a big problem. So I need both the limits exist, and I need the limit of my denominator to not be 0. That's really, really important. Okay, in order to split. Okay, so next is a power rule. Well, one of the power rules. We're going to learn 2 today. So if I have, oh, I keep doing that. So if I have f of x to the nth power, right? And maybe I know what the limit of f of x is, but once I raise it to the nth power, n being like some positive integer, okay, maybe then I'm like, I don't know, right? Trying to think of an example. Like how about x minus 2? So let's just do a quick example. So limit as x approaches 3 of x minus 2 raised to the 7th power. I do not want to factor that, right? That sounds like a nightmare. But because the limit of the inside exists, right? And I would show that, I would say something like limit of x approaches 3 of x minus 2 is 3 minus 2, which is 1. So, and with this limit law, I know that because the inside exists, I can bring the limit inside of the exponent. Okay, so that means that for my little toy example here, I get limit x approaches 3 of x minus 2 raised to the 7th, which is 1 to the 7th power, which is just 1. And so I feel like if we were in class, I would probably have somebody ask me, do I have to show this part of the work? And I would say definitely at this point, yes. I mean, maybe at some point you can just say the limit of a polynomial exists, as x goes to a finite number or something. We could talk about that once we get closer to the exam. But honestly, oftentimes this isn't even really extra work because then you can skip a lot of work when you're doing like the piece by piece up here. So like I got to skip straight from here to there. Or honestly, no, they do like you to bring the limit inside. Never mind. They do like you to show that. So definitely for right now, I definitely want you to show that. Especially, you should always be showing it when it's like a multiplication or a division thing that you're splitting over. Okay. Okay. So let me delete this. Um, okay. And then here, it's very important that n is positive. Integer. But an integer just is a fancy word for a whole number. So like the integers are 0, -1, -2, -3, dot, 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 and 1, 2, 3, dot, dot, dot. So positive integers are 1, 2, 3, dot, dot, dot. Okay. Because if n was negative, right, we'd also have to worry about the limit being non-zero, but I didn't mention that. Right, we can just use our division rule there. Okay, but how about if it's like a fraction, right? Like I don't know if y'all can hear the beeping and stuff, but hopefully not. Zoom seems to be pretty good at that. Um, so what if I have some root? Okay. Because, the toy example I gave before, which maybe I shouldn't have deleted and should have just brought down a little bit further, this could be a similar thing, right? I know how to take the limit of something that's inside of a like cubed root, fourth root, fifth root, 17th root, but thinking about the 17th root of it, I'm like, oh my gosh, just like breaking my brain. Um, well, if the limit of the inside exists, and one other thing that we need to think about, we can bring the limit inside. So again, here n is a positive integer because we're taking the nth root, so that's 1 over n. The other thing is remember, it doesn't make sense to take an even root of a negative number. Because like the square root of -4, we don't know what that is. Okay, at least not in this class, I should say. So, so if an even, then limit as x approaches a of f of x must be greater than or equal to 0. Okay, so if that's not true, then you can't bring the limit inside. But we don't usually get problems like that. Definitely not on an exam, and I'm not going to give you a question like that on a quiz where it's going to be like negative, and so it's a trick question because actually um, the limit of the inside was negative and you're taking the fourth root of it, so you can't actually bring it in. Any questions so far? Let me pull up the chat again. I wish it would just float on top of everything. Okay, so these are our limit laws. Let's do some examples. I'm worried if I cut it, I'm gonna forget to paste it again later. So let's just move it really far down. Okay. Okay, so let's do our first example. Sorry, I have my notes over here. I know I'm looking all over the place, but so for the first one, oh wow, I'm starting to sound like a person. That's great. Okay. Okay. So I have my first thing, and I'm like, woohoo! I just learned all these limit laws. Let's use them. The limit of a polynomial where x is going to just some constant number is always going to exist. So I know both these are going to exist, but I can't split this over division. Yeah, because I can show that both the limits exist, or I can just say that both the limits exist, but the limit of my denominator would be 0. So so now it's like, huh, okay, well, when my denominator goes to 0, my whole thing blows up, right? But only if my numerator doesn't also go to 0. So let's see. Um, and this is not something that you have to do every time. This is just me trying to show us how we could reason through something. Okay. So let's see. So limit as x goes to 4 of x squared minus 6x plus 8. So I know that this limit exists, but what is it? So let's see. So 16 minus 6 times 4, that ought to be 24 plus 8. Oh, interesting. So 0. So the limit of my numerator and the limit of my denominator are both going towards 0. So here comes uh, a I don't even know what to call this. Maybe like a rule or something, or a general rule. I don't know. But if limit goes towards 0 or 0, which I know doesn't make sense, but just bear with me. Like what? So the numerator is going towards 0, the denominator is going towards 0. I know it's illegal to write 0 divided by 0, or infinity over infinity and plus or minus each of those, however you want to do that, or uh, or like infinity times 0, something like this. Uh, need to do need to investigate more. Okay, because 0 over 0, that doesn't always cancel, right? I mean, that doesn't even really make sense when I'm saying it. So, and then infinity over infinity, that doesn't always cancel. Sometimes you get something that at the beginning it looks like it's going towards infinity over infinity, which, it is, but the whole answer is like 7, right? Or 0 times infinity. We don't know which one wins. Okay. It could be that we end up getting -1. So So whenever we get something like this, like a 0 over 0, infinity over infinity, 0 times infinity, that just means that we need to do some more investigating. But investigating usually isn't too crazy, right? It just means maybe try factoring or try rewriting it some other way. Okay. So let's try factoring. So what adds up to, we're doing so good. What adds up to -6 but multiplies to +8? Well, -2 and -4. Yay! Okay, cool. So now I get to cancel these two. And now I just have limit as x goes to 4 of x minus 2. Right? So my answer is just going to be 2. And some of you might have had that gut instinct from the beginning, and that's great. Um, but that we are going to get ones that are harder and harder and stuff, and I just want to build this habit. Okay. So we had something that looked like 0/0, but it ended up being 2, right? So it just goes to show you just don't know. Okay. What if we had something slightly different? And of course, feel free to interrupt with questions at any time. I might forget to ask for questions. Wait, I feel like I scrolled past one. Oh no, I didn't. Okay, limit as x goes to -2 of x plus 4 times x minus 1. So now I've already factored for us this one. Hmm. Well, this one, the limit of our top exists, the limit of our bottom exists, but it's 0. So we do feel like we have to be suspicious, right? And unfortunately, we can't just split over division because our limit of our denominator is 0. Okay, well, let's find the limit of our numerator. And so this one, I'm personally fine when it's a multiplication of two polynomials, especially these tiny polynomials. Um, I'm fine with you not showing that both of them exist and stuff. You can just rewrite it as -2 plus 4 times -2 minus 1. Um, and then we have 2 times -3 plus -6. Okay. Okay. But if I'm trying to figure out what my limit is, right? And I can't really use my limit laws because I can't split over the numerator and denominator. And I can't just plug in -6 for the top, right? Because that would be splitting over the numerator and denominator. What I have to do is I have to do my left and right limits. Okay. And then if they're equal, then that's what my limit is. If they're not equal, then my limit does not exist. So I don't know. Start with whichever one you want. Let's start with the right limit, I guess. Here's how I like to think about it. Um, People have lots of different approaches and stuff. This is always what made sense to me when I was taking this class, and I've had students tell me that they like this, so I hope that you all like this as well. Um, but how I like to approach this is I look at one piece at a time, right? So I know my numerator is approaching 6, -6. And my denominator I know is approaching 0, but I want to know, is it always positive as it's approaching 0, or is it always negative as it's approaching 0? And for a tiny piece like this, because remember, we're just coming from the right. Sorry, I'm not sure if I'm mirrored or not, but we're just coming from the right. Okay. So we're a little bit bigger than -2, but remember, bigger than -2 means like 1.9, -1.9. Okay. So, and you don't have to show, hold on, I'm gonna sneeze. Oh my God. Okay. Um, okay, so you don't have to do this, but definitely in the beginning, I think it helps. And I don't know, I kept doing it even after I started getting better at this stuff. So if I have -1 0.9999, right, or whatever, plus 2, because this is a little bit to the right of -2, -1.99999, right? This is going to be positive 0.0001, right? So it's a positive thing. And this is actually 1 over 10,000. So for this instant, we'll have -6 divided by 1 over 10,000, which is -60,000, right? So we're getting humongously negative. Okay. So really for me, like, here's what I would do is I would write this out for me to remember, okay, yeah, positive, right? And then this other part is just helping me remember, oh, as my denominator goes towards zero, my whole thing explodes either to positive infinity or to negative infinity, right? So so I have a negative, and that's what, so that's what this part is helping out with too, is this is negative, right? So we have a negative over a positive and we're exploding. So what are we exploding to? We're exploding in negative infinity. And you don't have to do a test point. You can just, I mean, there's so many different ways that you could show your work for this. Um, you don't have to do a test point. I'm happy with you just doing the approaching -6 and approaching zero and positive. I'm fine with that. Okay. And then you get equals negative infinity. You could also look at solutions to previous exams to see other ways that other people do work to show this stuff, but this is what I like. Because then I have all my information just like right there, readable. Okay. So how about my left limit? X plus 4, x minus 1 over, what was it, x plus 2, I think? Yeah. And now this one approaches -6. This one approaches 0. And negative. Right? Because if I'm to the left of -2, that means I'm like negative 2.1 or something, right? So, so I'm exploding and I'm a negative divided by a negative, so two negatives cancel to be positive, so I get positive infinity. Okay, so why was I doing all this? Oh, right, because I wanted to figure out the limit as x approaches -2 of this function. Well, I wasn't able to figure it out just by looking at it, so I took the left and right limit, and my left and right limits do not agree, right? Infinity is not equal to negative infinity. So, right. So this does not exist. Or DNE. Questions? Okay. Um, maybe I'll do that one later. Okay. Another example that I want to do is the limit as x approaches 0 of 1 over absolute value of x. I also want to do limit as x approaches 0 of absolute value of x divided by x. And that's it. Yeah. Okay. So for this first one, kind of, so, and once again, there's just always this thing of there's so many different ways to think about stuff, right? There's so many correct ways to think about things. I mean, there's plenty of wrong ways, right? Probably infinite wrong ways, but probably also infinite correct ways. So, one way that sometimes people think about absolute value of x is they say, okay, well, this is x when x is greater than or equal to 0, and it's uh um negative x, sorry, I got myself confused for a second, when it's less than 0. When x is less than 0. Because what does absolute value do? If you're 0 or you're positive, it just returns itself. But if you're negative, it makes it positive, right? So if x was -2, -2 would be +2, right? So sometimes people like thinking about it like that, but once it's like absolute value of x minus 2 or something like that, you have to be more careful about like, okay, so if it was, so let's do that example, I guess. Right, then it's x minus 2 when x minus 2 is greater than or equal to 0, meaning x is greater than or equal to 2. And it's negative x minus 2 when x is less than 2. To me, I don't know. To me, this never really felt very helpful. And so then you can like kind of split it. Um, so this one would be more for if I asked you the question like limit as x approaches 2 of 1 over absolute value of x minus 2. Right? This is sort of another scenario that could happen. Not the scenario we're focusing on right now, I guess, but nevertheless. So what was I saying? I don't remember. Oh yeah. So if you look at the solutions on the previous exams, I think this tends to be how they talk about it. They like talk about the function of absolute value of x or absolute value of whatever the thing is. For me, I don't know. For me, I just think about it like I do the because when it gets really hard is when it's not just 1 over absolute value of x, it's like the second one. So how I think about it is I do like the limit from the left and from the right. And so I know that this is positive, right? So as x approaches 0 from the right, I know that that's always positive. So I know that this is because this is so I guess I am using this idea here. Oops, sorry. This idea here. It's just I don't usually write it out like that. So this goes towards infinity and limit as x approaches 0 from the left, 1 over absolute value of x is, and that's the other thing that you could do. You could just be like, you could use my trick that I use. So approaches 0 and positive, right? And you can say, okay, this is, or you could say limit as x approaches 0 of 1 over negative x, right? But x is negative. See, this is why I don't like this version. I just like to say, okay, this is approaching 0 and it's positive, so this is going towards infinity. That's sort of my my take on it. Okay. So then the left and right limits agree. Therefore, the limit is infinity. The other way that you could think about it is like, so you need to show work, right? But like the way that I would reason through this is, oh, what's the problem for 1 over x? And again, I'm sorry, I'm not sure if I'm mirrored or not. So I might be drawing the backwards one, but with my hands. But so 1 over x, right? As you approach 0 from the right, you go up towards positive infinity, and as you approach it from the left, you go down towards negative infinity. But if I absolute value x, then both sides are going to go towards positive infinity. Okay. So that one hopefully is not too bad. And I probably explained it more than it needed to, but it's because of examples like this next one, right? And then I'm going to do another one that's even harder than that. Let me move this out of the way. So for this one. So for this one, our gut instinct, right, is to cancel the x's. That's like immediately what I want to do. I'm like, I've got like I got 0 over 0. Danica told me to investigate more. And part of that is like factoring or canceling if I can, blah, blah, blah. I'd love to cancel these. These are not always equal, right? So for x equals -1, they don't cancel because absolute value of -1 is +1, and x equals -1 means we're -1. Right? So absolute value of x over x is not always equal to 1. Maybe I'll say not always. Well, let's just write it's not equal to 1 because it's not always. Right? So for example, absolute value of -1 over -1 is equal to 1 over -1, which is -1, which is famously not 1. Okay. Because I get it. Gut instinct, cancel them. And usually this is a question, there's a question like this on the midterm. I've seen it a couple of times now. And it always breaks my heart when somebody cancels. Because it's like, yeah, that feels right, right? But it's not correct. So, okay. So what we could do is we could do it the way that I kind of talk about it, where you just sort of like start pointing at things and say where they're going to and and if they're positive or negative. Or you can use this thing, right? I I'm happy either way, right? I think you should figure out what works best for your brain and run with that. Okay. So, limit, but either way, we got to do right and left limit. Okay. If you're not able to figure out what a limit is, you have to do the right and left limit. Okay, so right limit. So my approach would be, I would say, goes to 0 and positive, because it's always positive, right? Goes to 0 and positive. And then I'd say that they cancel because they're both positive. Or you could do something that's probably a lot cleaner than just my weird vibey thing that I talk about. You can say because of this, right? And so you should write that somewhere, if only just to remind yourself of what the heck's going on. And we can just rewrite top thing as x. And now they cancel, right? X divided by x, that is 1. It's just the absolute value of x divided by x is not always 1. So we get 1. Okay. So this one goes to 0 and negative, goes to 0 and positive, right? So how I would use the absolute value thing is I would say limit as x approaches 0 from the left of negative x over x. So I get -1. And and remember, I'm canceling, yeah, I guess I'm skipping a step, sorry. So once I have limit, and you can skip this step, that's fine with me, but maybe I should write it out because we're just learning this for the first time. Probably be a good teaching technique. Okay. So you cancel those, so you get 1, but x has nothing to do with 1, right? So this is just 1. So yeah, so I apologize, I did skip that step, but that's secretly what's happening there. And so 1 is not equal to -1, so this one actually does not exist. Questions, comments, concerns? Okay. So, another example, and something like this has been on the exam like a couple of times. X approaches 2 from the left of x minus 2 divided by absolute value of x minus 2. Okay. So, it really is. It's tempting uh, to just cancel those. That's not the case, right? So we know from the thing that we just did that this is not going to exist, right? And that is, well, sorry, the limit would not exist, but they're specifically just asking for the left limit, okay? And so I think probably why they asked for the left limit is because this is the trickier of the two. And so I'm happy for you to do it my way, right? Where you do it like approaches 0 and is negative, approaches 0 and is positive, and then get -1. But how they do it on the solutions typically is this way. So they'll use this and they'll say, okay, well, um, the uh, we're in the scenario where this inside piece is negative because we're approaching 2 from the left, so like 1.9, right? But 1.9 minus 2, that's going to be negative. Okay. And so we have limit as x approaches 2 from the left. We leave the top the same, but now the bottom is negative x minus 2, because that's how we make it positive, right? We're looking at this part. Okay, we're coming from the left to 2 again. Sorry, I don't know if I'm mirrored or not. We're coming from the left to 2. So, so x is less than 2. And, you could distribute that negative, but I would just cancel these two, right? So I would cancel them, and then we just get a -1. That's -1. But again, if you explain it the way that I did it above, like with the goes to 0 and blah, 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 that's fine with me. I'll still give you full credit for that. Questions? Okay, so there's like a fact that I would just recommend that you memorize. The proof of this is quite complicated. You can look it up if you'd like, but I would recommend that you memorize this. They often have this somewhere on the midterm. So it's the fact that the limit as x approaches 0 of sine of x divided by x. So it looks like it's gonna be 0 over 0, right? But somehow these cancel out to be 1. Okay? Again, just not obvious. And it looks like this example that I wrote down, that this should also just cancel to be 1. But that's actually not the case. So really, the fact that maybe we should be memorizing instead is that limit as x approaches 0 of sine of ax. Maybe I need to give myself more space. Divided by ax equals 1. A some number. Okay. So really it's not just that I have sine over x, right? It's that I have sine of something divided by that same something. Okay. Um, those somethings both going towards 0. So here, what I want to do is I want to make my denominator look like 8x, right? I want to make my denominator 8x, but I can't just multiply my denominator by 8. That's going to change the number. But what I can do is I can multiply by 1. Okay, just maybe a funky looking one. And so maybe I'll write the 8 out here. Okay. And remember, I know that the limit of this piece exists, so I can pull the constant out. For something as simple as like pulling out the constants, it's okay with me if you don't show that the limit of the inside thing exists. If you're just pulling out the constants, the ones that I really, really care about are the multiplications, the divisions, and the power rules. Okay. And now this I do know. So oftentimes students will cancel out the two 8x's. That does not make any sense. The 8x is inside of sine. All right, so sine is a function and it has been fed 8x. Okay, so sine of 8x over 8x does not cancel to just sine of blank. Okay, that doesn't even make sense. I don't even know what sine of blank is. Okay, sine is a function. So for it to be a number, you need to give it a number. Okay. Okay, just wanted to show you this because there's often something to do with this on the exams. Questions? Uh, okay. Vertical asymptotes. So sometimes we want to know if a function has a vertical asymptote. So remember, vertical is the up and down one because horizontal looks like the horizon, like you're looking over the horizon. So vertical is up and down. So oftentimes we want to know, does something have a vertical asymptote? Yes or no, right? So what you can do to find vertical asymptotes, so to find, well, oh, that's right, I forgot I already had some stuff. Mm. So there's a couple of drawings, right? So it could be that your function, as it's reaching the vertical asymptote on both sides, shoots up to positive infinity. It could be that on one side shoots up to positive infinity, on the other side shoots down to negative infinity. Or both go down to infinite to negative infinity, or the first side goes down and then the second side goes up. But if we think about these in terms of limits, right? This is like your left or your right limit is going towards infinity. Um, Forgot that I already had some of this written. Okay. So what we're going to do is we're going to use limits to find the vertical asymptotes. Okay. And so remember, vertical asymptotes are lines x equals a. Okay. So vertical asymptotes look like x equals a. And these are outside the domain of f, right? Where f of x is our function. Um, okay, so to find if a function f of x has vertical asymptotes, want to see if it has one of these pictures, right? But if we look at one of these pictures, it's like, okay, well, like, is it shooting up towards positive infinity or shooting down towards negative infinity on one side or both sides? Who knows? Okay. So the big tell is, do I have wow, no, I can't even. Oh yeah, what's outside of my domain, right? But x equals a, that has to be an a that's not infinity, right? X equals infinity doesn't even really make sense, right? The only reason why limit equals infinity makes sense is because limit is talking about where we're heading towards. Because infinity is not a fixed number, neither is negative infinity. So, okay. Um, so like the first thing that we want to think about is what what when is my denominator zero? So look for how about when denominator is zero? That's probably a better way to say it. Look for when denominator is zero. Okay. That's kind of our first step. And then we want to look at our left and right limits of that. Okay. Because for example, if we go back to, and I can't remember what that function was, but if we go back to that first example that we looked at, so maybe I'll say recall. Because we've looked at this function today, and I'll factor it already for us. So we do have, so 4 is not in the domain of this because we can't divide by 0. Okay. So denominator is 0 at x equals 4. But the limit as x approaches 4 of f of x, as we showed above, right, is 2. So not a vertical asymptote. It's just not on the function, right? So it's this sort of weird thing, and my gut instinct is to always just start canceling, right? Because that's kind of, I feel like that's what we've been trained for, blah blah blah. But in fact, f of x does not have 4 in its domain because you have to look at the original function that it was. Okay. So f of x is a line, but it's a line with a hole in it at x equals 4. Okay, it is the line x minus 2, but just with a hole. Okay, so it doesn't have a vertical asymptote. Whereas, almost like I planned this or something. No. If we recall the next function we talked about, I'm just going to keep using the same name, sorry. So x plus 4, x minus 1, divided by x plus 2. So denominator is 0 at x equals -2. And, we'd have to go through and like show our work and stuff, but since we already have, I'm just going to recall it for us. As x approaches -2 from the right, from the right is negative infinity, I think, because we have negative over positive. Yeah. So now we know it is a vertical asymptote, right? But maybe we want to know the full description. Again, the only reason why I'm skipping all this work is because we've already done this work. So let me double check that I did that right. Yep, okay. So f of x has a vertical asymptote. And so by the end of this semester, we're going to be not only looking at this, but we're also going to be sketching the graph. Okay. And that is, I think, probably always going to be on the final, is sketching at least one graph. Okay. So it's not enough to just do, so that's why I'm trying to get us in the habit of doing both sides, is because then we'd be, so like for the exam, or for the quiz or whatever, homework, blah, 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 we'd be like, okay, as it approaches -2, so this is x equals -2. As it approaches it from the right, I'm going to shoot down towards negative infinity. As I approach it from the left, I'm going to shoot up towards positive infinity. Right, and we do a bunch of other things as well, but we'll talk about that later in the semester. But yeah, this is really important question. So right, so for this example, the limit didn't exist. So you're right that like this kind of looks strange because the limit didn't exist. So like, but I still have this vertical asymptote. But my limit on either side, they disagreed, but they disagreed in a way where one was going towards positive infinity and the other one was going towards negative infinity. So like if they disagreed because one side was going towards 3 and the other side was going towards -1, that's not a vertical asymptote. Because vertical asymptote is like you're like shooting in some direction, right? Like, I don't know. Does that make more sense? Okay. So these are two very important facts, right? Theorem is just like a really fancy word for a important fact. Important facts, I guess, here. So let's focus on the first part first. Oops. Oh. So if the function f is less than or equal to the function g when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then their limits have this relationship with each other. Okay. So let's break it down. Let's break down what the heck's happening here. So near A just means like around A. So A is going to be somewhere on our number line, right? Because A is just some value, some number. And so they're just saying that like, okay, a little bit to the left and a little bit to the right of A, except maybe not exactly at A. Um, any of those numbers in that purple, except maybe actually plugging in A, uh, F is going to be less than or equal to G. Okay. So, okay, so that's that first part. Okay. And then we need that the limits of f and g both exist, or else what does it mean for does not exist to be less than or equal to something, right? That doesn't make any sense. Or does not exist greater than or equal to something, that also doesn't make any sense. So basically what they're saying is like, okay, if around A, like a little bit to the left, a little bit to the right of A, except maybe not right at A, because remember, sometimes we can have jump discontinuities and stuff. We can have some weird, funky things happening. The F is always less than or equal to G, then, and their limits both exist, then as as you approach A from the right and from the left, right? F is my index finger here. Oh, sorry. G is my index finger here and F is my thumbs here, right? As I approach A, right? Maybe sometimes they're equal and stuff, and maybe something weird happens right at A. Maybe they have jump discontinuities that are funky. I don't know. But their limits are going to still be, G's limit is still going to be bigger than or equal to the limit of F. Because G was always bigger than or equal to F, right? So it's not, nothing weird's going to happen right as your limit approaches there. It's something weird could happen in the function, right? I could have like, here's my G, and here's my, so this is G, and here's my F, right? Maybe they're equal here, and then jump discontinuity, and then maybe later on F is bigger. I don't know, right? But around A, so here's X equals A. And maybe they don't even, maybe A is not even in their range, in their domain, but maybe it's like something like G's point, G of A is way down here, right? And F of A is way up here or something, right? Maybe something weird happens, but those jump discontinuities don't do anything to my limit, right? If I take my limits, right, it's still, because remember, when I'm taking my left and right limit, I start a little bit to the left or a little bit to the right of the point A, and I just see where I'm heading, okay? So hopefully this makes some sense. And then why is this so helpful? Well, this is extremely helpful because now we're going to use the squeeze theorem. The squeeze theorem I recommend that you memorize. This is extremely powerful. This is extremely helpful. They often ask about it on the exams. And this is something that if you go on to higher calcs, you're going to use again and again and again and again and again. Okay. Okay. So now we have three functions. Okay. So for these three functions near A, but except maybe exactly at A, because there could be something weird that happens at A. Okay. If you have this relationship with each other where F is less than or equal to G is less than or equal to H on that around A, but except maybe at A. And not only do the limits of F and H exist, but they are equal to each other. Okay, they're equal to each other. Sometimes we call that L. Then the limit of your function in the middle also has to be L. This is why they call it the squeeze theorem, because you have this relationship where you have like H is the biggest, G is in between, and F is the smaller of the two. And they have this relationship that around A, except maybe exactly at A, right? They have this relationship with each other where one is bigger than or equal to the other and so on, right? But somehow F and H crunch in such that their limits not only exist but agree. Well, G was between the two, right? Maybe G was bouncing around. I don't know what G was doing, but G was between the two, and then the two sort of squeezed in and became equal, right? Their limits agree. So then G's getting squeezed in between them. So then G's limit also has to be that. Okay, so that's kind of like the vibey reason as to why this is true. Okay. But why is this helpful? This is helpful because there's going to be a lot of times where they're going to hand us something and we're going to be like, geez, Louise, I don't know. I don't know what the limit of this thing is. But then you think about the squeeze theorem and you say, okay, but I do know a function that's always bigger than or equal to this function and a function that's always less than or equal to this function. And I know how to take the limits of those ones. Okay. I know it's kind of hard to visualize it when I haven't like given you an example, but if we have time, I will give you an example. So that's why this is helpful because usually we're handed a G. They're like, find the limit of G. And we're like, geez, Louise, I don't know. So then we produce an F and an H such that we can use the squeeze theorem to figure out what G is, the limit of G is. Okay, so that's what's going on here. And once again, I don't expect y'all to fully understand this on the first go around, right? But thankfully we'll have practice with it. Where's my picture? So this I stole from your textbook. So I really, really like this picture. And so here we go, right? Well, let me show the squeeze theorem as well. So around A, except maybe not at A, because maybe there was a weird jump discontinuity or something. H is always greater than or equal to G is greater than or equal to F. Okay, that is true, right? If I look at like this, I can even make it bigger, right? I just can't go past that crossing line, but that's fine, right? That's pretty far away from A, right? I could just look at just like this area. Okay. Oh. Um, so, and I know that the limit of H, right? If I do my left and right limit, I get it to be L. If I do my limit of F and my left and right, I get it to be L. And pictorially, this feels like, okay, well, I can just trace it with G, right? But usually the problem is we don't have a picture. So the one that I forgot to copy and paste the pictures. Oh my God, okay. So the example I want to do is, oh, okay, yep, no, now I remember it. Now I remember what the example was. I thought I had copied and pasted it. It's okay. Limit as x approaches 0 of sine of 1 over x over x. So, you know, fair enough. Maybe you're thinking, oh, I gotta use the that thing that we talked about before, but not quite. Not quite. Sine of 1 over x as x goes to 0 is does not exist. So let's think about that first. this is like, so as x approaches 0, 1 over x is approaching either infinity or negative infinity, depending on which direction we're going in. But remember, this does not exist. And neither does as x goes to negative infinity. Because remember, they just keep oscillating forever and always between 1 and negative 1. So it's not like approaching anything. It just keeps oscillating as it keeps going. So this one like really doesn't exist. So I can't use that rule that we used above because that fact that I'm asking you to memorize. I can't use division, like the division rule. Even if I did, I'm not even really sure what to do. I've got DNE over 0, right? Like that's, I don't know what's going on with that. So this is an example of what the heck is happening, right? So what do we do? And this is a fact that we leverage all the time in mathematics, all the time. We're going to leverage it in this class. You're going to leverage it in all the other calculus classes that you take. If you continue to take math classes, you're going to use it there. Like it's just it's a useful fact to remember, and it's powerful. Okay. And what is this fact I keep telling you about? Sine of any function, I'm just going to say f of x. There's nothing you can plug in to sine that can make it less than negative 1 or bigger than positive 1. Sine is only between negative 1 and positive 1. You can times it by stuff on the outside. There's nothing you can plug into sine to make it bigger or smaller, right? It is always between negative 1 and 1, inclusive. Okay. Okay, Danica, so this is just like a powerhouse. This is like the fact that the mitochondria is a powerhouse of the cell. This is revolutionary, right? This is, and it's the same for cosine. Well, revolutionary makes it seem like it's brand new, but this is powerful. This is like you should probably have a screwdriver in your house, right? Because you never know. Okay, so for us, for our example, I'm sorry, everybody, x squared times sine of 1 over x. I mean, all this stuff that I said before is still true, right? Except now it's the product rule. So the product rule we can't use because sine of 1 over x doesn't exist. And this is the same, except now we're multiplying all sides by x squared. Ay, 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 sorry, friends. Okay. So the minus is on the outside, right, of this x squared. Okay. Oops. I also need it on my sign. Okay, my bad. All right, here we go. Started doing the other one in my head and I was like, this is not the one I wanted. Okay. So now I have my F, my G, my H. Okay. And the limits of these other two, I definitely know how to take those, right? So limit, and you have to show them, okay? But it's not that bad, right? This is just 0 squared, which is 0. 0 squared, 0. So now I say by squeeze theorem. And this is important that you say this as well, right? Um, Okay. So super easy, right? Like we went from a question that looked like 0 times DNE, which I'm like, I don't know what the heck that's supposed to be. Um, because I'll also tell you that 0 times infinity is not always 0. Okay, in a limit, in limits. Okay, because like for example, you could have x squared times 1 over x as x goes towards infinity, and that's gonna cancel to be x, and then you get infinity, right? But it looked like 0 times x to begin with. So we definitely can't guarantee that 0 times DNE is going to be 0, but in this case it is.